Well, hi folks, it's Cliff here, a toolmaker from New Zealand. Welcome to my shop. I'm going to be doing some spherical turning, some ball turning with this basic little radius turning attachment made out of a cheap boring head. I'll be doing a bit of internal spherical machining with this little tool, cutting an internal sphere for a ball and socket type joint. A very fascinating subject. Please stay tuned. I've always wanted to have a go at making and using a radius turning attachment or a spherical turning attachment, and so I started studying online. That's so time consuming, isn't it? I looked at all the different designs that I could find. I found about 30 different YouTube videos on all different designs, and R&D is so important before you start a design, to gather everybody else's ideas into your head, sketch out the pros and the cons. Look at the relative merits, look at the manufactured products that are available especially, and try and get a feel for what all the different options are. But you know, there's about 30 different designs. Some of them are based on horizontal rotation, some of them are based on a vertical rotation, and I can see pros and cons with everything, and begin to realize that I just don't have enough experience to sift through the designs and work out the best one. So I thought, why don't I just bash something together out of bits and pieces that I had in the shop: an old Chinese boring head, a little bearing block, put a tongue on it, pop it into the quick change tool post and have a go. You know, just machine up some parts. Make up some spheres, some internal spheres, some external spheres. Get a bit of a feel for what can and what can't be done. How small can you go? You know, what are the issues? What are the machining loads like? What are the geometrical challenges and clearance limitations? And so I'll be doing that in this video and showing you what I've learned. So let's just go through basically what this is. It's just thrown together out of a few bits and pieces I had in the shop. So it's a cheap Chinese boring head that I put a TTS 3/4 inch parallel shank on. I had an angle plate with a 3/4 inch bore in it, so I've just popped it into that. I made up a couple of collars and drilled a hole on an angle for that hand wheel. So I really just threw it together out of a few things I had sitting in the shop just to try the idea out. So looking at the tool up close for internal work, so you can see there it's got a 12mm shank that goes into the boring head. I've turned it down to 6mm and put a cross hole of 4mm to take a 4mm carbide. Got a whole stack of broken carbide end mills that I inherited, so I just ground that angle there. Oh, I just bumped the lens. I hope I didn't scratch it. Out of just diamond ground it to that sort of geometry there, and that's enough clearance to get down to about a 7mm radius sphere. So it's pretty basic. It's just got a little tongue screwed on the side there, a real lash up thrown together out of bits and pieces to try the idea out. It's not optimal. I found I needed to tighten up the bearing with this adjustment and snug up this way so that there's absolutely minimum clearance. So it's quite snug there, any clearance, and the tool sort of springs away and gives issues. So that is as expected. It needs to have a close fitting bearing. So I'm doing some trials here, machining some steel balls, 21 millimeters diameter. I'm putting the cut on by having the tool set with too big a radius and then reducing it down in a series of cuts to the finished size. I'll do a couple of cuts so you can see it in operation. I'll have to back away to put the cut on so I can rotate to get at the adjusting screw, and I'm putting on a cut of 0.5 millimeter on the radius. I think that's what it is. Come back over center again. It's a bit time consuming, but that's just the way the boring head is orientated. Anyway. Now for the finishing cut, I really need to adjust it in position so I can feel when I'm close to the diameter. So I've got to put an Allen key in on the underneath. Yep. And rotate it. Well, that's about there. So that's about cut number 5 or something. You can see there's a little excuse me, there's a little bit of spring there, but it's given a pretty good finish. Machining steel with a high-speed steel tool, cutting on the end of it, which gives us good stiffness. Yeah, it's working pretty well, really. Quite a quick process. So you can see some of the limitations here. I'm learning a lot. So you can see where the ball is connected to the mandrel, as it has to be a diameter of a certain strength there. And that is contacting on the heel of the cutter at that point. That's with a 90-degree angle on the face of the cutter. Also, there's a limit to how close you can get to the chuck. I'm only a few millimeters away from the big 3-jaw chuck here, and that means it has to project out a certain distance to give the clearance. But overall it's working really well, and I'm learning a lot. Alright, now I'm going to try a bigger one, about 25 millimeters diameter. Those smaller ones have come out quite well. You can see there the little lip where the tool couldn't quite go to a small enough diameter. It doesn't matter for this application, or I can just machine it off. But of course these are just cosmetic parts, just balls for handles. If you are machining something high precision, you know, for a ball and socket joint or something, you'd have to have a much deeper understanding of the settings of the different geometries, the different tool radii, the profile of the cutter, and the accuracy of all the different positional settings and so on. And this is really just general background learning for me, and if I do get to that type of work in the future, I'll have a look at this video, learn all I can, and then see if I can take it a step further for the necessary high precision ball and socket machining. But I may never have to do that, and so this is just preliminary learning for the interest of it, and to make a video for you guys. A few lines are starting to develop, and I think that's because the bearing adjustment is starting to wear, and we're getting a little bit of the beginnings of slop in the bearings. And so note to self, for this to work for high precision spherical turning, the rotational tool must have very accurate bearings, very well adjusted bearings. If there's any slop in there, is going to start to cause lines and errors in the radius. So these are my first trials of machining a concave sphere. So some of the things I've learned is it's easier to run the lathe backwards and cut up from the bottom So the tool is a 6mm shank stepping down to a tool bit of 4mm diameter. Ground into a V with a radius on the end, and then that 6mm enlarges out to the 12mm boring bar bore, held in the end with a grub screw, and just coming up from the bottom, it cuts really well. Just sweeping round to the center line, and then I can set my digital readout to Z0 and either go in deeper with each cut or change the radius to a larger radius with the boring bar with each cut until I get the spherical diameter that I want. Alright, well, let's go a little bit deeper. So I'm taking depth in the Z, the longitudinal, of 0.2 at the moment. Give it another 0.2. Oh, the shank of the tool's still not up against the end of the bar, but I haven't quite got enough clearance in the transitional radius to the 12mm diameter. But I could go, yeah, another 0.5 mm deeper. So that works really well. It's a really enjoyable feeling of cutting around an arc. Quite amazed at how well that works. So this opens up the possibility of machining ball and socket swivel joints. All sorts of possibilities. Oh, I wonder how it goes on smaller radiuses. I've set this on about 7mm radius. Wow, that's another tool I should have made years ago for my plastic injection molds, nozzle seats, all sorts of radii for nozzle seats. I could have just dialed them in. I couldn't find many examples online of internal spherical machining or socket machining. And I was just sketching it out and thinking, how deep can you get? You know, I think you're limited by the shank diameter coming up against the end of the part. And in this case, I made a very slender 6mm shank with a 4mm tool, and that works really well, and that allows you to get within 3mm of the end of the part. So if it was set to a 20mm radius, you could cut a 17mm deep spherical socket. There's a smaller one there. So it works really well, but you can't go in a full half sphere with this system anyway. Well, I'm so glad I made this rough knock-up to try the idea out. You know, you can do all the research in the world, study something online, but you just don't have an intimate enough understanding of all the different parameters to choose a good design and refine a good design. Well, I anyway need to really have a go at it and get a feel for it at a deeper level and combine that experience with the study to begin to have a chance at coming up with a good design. For external machining, the cutting forces are really good because they push in the direction of maximum support, because you're cutting, in this case, on the end of the tool as it describes that arc. So it's pushing lengthways on the tool, and so it doesn't need to be so rigid in the other directions. So just looking at that, it's a piece of 6mm high cobalt, high speed steel. So I tried just cutting initially with just a spherical cylinder shaped tool, if you like that, but I ground a bit of side clearance on it, and that cut all right, but soon found it's a lot better if I ground it with a 90 degrees flat either way, and a bit of clearance there, 2 or 3 degrees clearance there, and a little radius on that corner. That seems to cut really well. So that's just ground out of high grade, high cobalt, high speed steel, and even for machining steel, it seems to be lasting really well for the external machining, because it's loaded lengthways, so it can be easily reground by just grinding off the end. So that's really fortuitous, the way the load directions go with this type of horizontally rotating radius tool. I could make an improved version by getting around some of its inherent weaknesses by using this boring bar. This would make a better bearing. I could have a tapered fit bearing, which would be longer. I could thread this drawbar boss here with a couple of adjusting nuts and put a stud inside there with a handle on it further out. That would improve a couple of the weaknesses of this one, but it's still got the problem of too much length here in the body and the adjusting dials on the wrong side. It's always a dilemma, isn't it? Do you improve something a little bit, or do you go for a total solution and really put in a lot of hours? And I don't know. Anyway, I've got it here to remind me, maybe a future project. Well, I pressed on using the radius turning attachment to make these little ball-ended tap wrench handles, and it's fine for something like that. It machines to a nice finish, and it's an enjoyable machining operation, but I mainly did it so that I would learn about what are the critical factors in making a radius turning attachment that could be used for high precision work. And this system has got some real strengths. It uses an existing cheap Chinese boring head. It's graduated here. This system of tooling works really well. I've got a split bush there, and the tool pressure is on the end, so it's very stiff and rigid. That system of a 90-degree tool works really well. The weaknesses are that this length is too long. These boring heads project too far from the bearing. And it's the same problem when they're used as a boring head in a milling machine. The more length you have here relative to where the bearing is, the more flex and clearance magnification you get and issues you get. And you need good accuracy and stiffness to do accurate machining. So this length is too long and the bearing length is too short. It needs a longer bearing and a shorter boring head. And so it makes me hesitate to improve just this length of bearing problem because it still has got too long a head. The other problem is that the graduated dial is underneath where the off-center bore is here on the top of the part. The graduated dial is underneath, so that makes this boring head not at all ideal. The same goes for this other one I've got. It's orientated the wrong way. But it's got a lot of features and design characteristics that really are promising. It's just that it's not quite applied right in this particular setup. I don't know, this may be a classic case of I'll mull it over for a few days and then I'll come up with a design and I'll make it just to prove to myself that it would be a lot better. But it may be that I'll just run out of steam on it and get on with something else. But at least I've been able to document some of the key points. If some other folk out there are wanting to design something, or if I want to do it myself in the future, I just need to rewatch this video. Thanks for following through this design discussion video with me, and I appreciate your comments, and please like and subscribe if you're not already subscribed, and stay tuned for the next video. Cheers.